Olá! A IUPAP, International Union for Pure and Applied Physics, está interessada em muitas coisas. Dentre elas, a definição das unidades básicas que nós usamos no dia a dia, a manutenção das constantes fundamentais, mas também está muito interessada nos desafios que a ciência tem atualmente. Na área da física são muitos os desafios. Nós temos desafios desde o entendimento das partículas elementares, da matéria condensada, na física nuclear, na biofísica, na astrofísica. Em todas as áreas, ou sub-áreas da física, nós temos desafios. Para que você saiba quais são esses desafios, a IUPAP organizou um workshop especial, que chama-se Entendendo os Desafios da Física Moderna. Cada área da física está aqui sendo apresentada por um líder, membro da IUPAP, e que você terá então agora a chance de entender, através desta apresentação, os desafios que a área apresenta e como os físicos, de um modo geral, estão superando esses desafios para que a física seja um instrumento de entendimento das ciências naturais e que auxilie o homem não apenas a avançar o seu conhecimento, mas a tornar a ciência um instrumento útil da melhoria de vida de cada um existente nesse planeta e nesse universo. Assista e também faça parte do entendimento dos desafios da física moderna. Boa sorte!
So, next speaker is Toshiyuki Azuma and speaks about AMO physics, diversity and specialty.
So thank you, Chairman. Today's my task is, again, briefly introduce about the recent activities in atomic physics. Of course, AMO physics, I'm sorry. AMO physics is usually atomic, molecular, and optical physics. Then usually for the particle physicist or nuclear physicist, they said, okay, it's dealing only with the electromagnetic interaction. Of course, it's most well understood interaction. However, as we learned today's talk by the David Wineland, or yesterday's talks by the Bill Phillips, there's many of new findings now. It's really we are enjoying. Then another point I really want to emphasize is AMO physics is really closely related with the other field. For instance, Bill Phillips emphasized that AMO physics is really correlated with the solid state physics now. And of course, we use a molecule. So molecule is really, physical chemistry is related. Then now the laser facility is really important, so optics is now the critical issues. Then astrophysics or fundamental physics, or just now we learned nuclear physics or plasma physics. All of these sciences are really closely related with AMO physics. So from our viewpoint, AMO physics is just at the center of the physics. Then I will start with some relation with astrophysics. Now this is a very recent data took by the X-ray satellite Hitomi. They are launched to observe the birth of the galaxy. That's one of the main tasks. And try to observe the hot wind of the galaxies. But in reality, it was very soft. But how they detected? They simply observed atomic spectrum of the iron atom. From the Doppler shift, they estimated the speed of the wind. So atomic physics is critical in this observation. Other example is, again, my friends observed recently using the ARMAS, or many arrays of the telescope at Chile. And my colleague observed the rotational spectra, rotational band of the molecules. From this Doppler shift, she clearly observed the rotation or rotational moving of the molecules just the point of the baby stars. Such information also can be obtained from the molecular spectrum. Or maybe if I said about the fundamental physics related issues already introduced by the previous speakers, for instance, anti-hydrogen. Yes, this should be the nuclear physics, not nuclear physics, this is atomic physics. Then recently, the people succeeded to measure the 1s, 2s, 2-photon laser spectroscopies to check the CPT violations. In the precision, this stage is 10 to minus 12. So using our technique, people can understand the fundamental physics. Then I have to explain a little bit about the front end of our communities, but of course, it's a very tough job. Then I decided to just refer the recent major conference in our communities by IUPAP, supported as a Type A conference. We have ICAP and ICPIC. ICAP dealing with mainly atomic physics. Then ICPIC deal with atomic collision process, so dynamics. Then every year, again, we celebrate Young Scientist Prize. So we already have more than 10 winners in the last several years. The keyword of this winner is, one of the keywords is ultra gold. Okay, so maybe more than half people, including the people from NIST, they are dealing with ultra cold gas. The reason why they could do such issue is, yes, we already done very well in this conference, because now we can use a magnet MOT trap, or optical lattice, or ion traps, or ion storage ring. These devices enable us to deal with such cold systems. Then the major interesting issue is, of course, BECs, or BCS crossovers, or quantum simulators we already learned, or dipole quantum gas, or Udall blockade, or quantum computings, or optical clock. Many, many variety of issues. And another typical keyword is ultra fast and ultra intense. So among the winners, 1, 2, 3, 4. 4 prizes go to related with these issues. And this is because advance of the ultra intense lasers or recent XFEL. Because of that, we can enjoy the attosecond scale science. We can follow the motion of the electrons in the systems. Or using the X-ray regions, even in the X-ray regions, we can enjoy the optical control. Then people are interested in this issue very much. But now, I really want to show my interest. And then you can understand how it's related with typical optical field, with the other field. My issue is, one of my issues is atom plus light. using the high energy accelerators. Then other issue is the molecule plus light in the slow energy ion storage ring. But for both of them, the key word is cooling. And today, I will show this example. And of course, I already told you the trend in X-ray is, yes, using the lasers, you can produce the X-ray lesions light using technique of the high harmonic generations. Or recently, maybe the more than 3 X-ray FEL is available in worldwide. That makes this field very popular. But just think differently. Using the tiny, thin silicon crystal. Then using the high energy accelerators. In this case, we started with medical therapies heavy ion accelerators built in Japan. And usually, this machine is dedicated to the cancer therapies, so it's irradiated to the brain or cancer areas. However, my case is just irradiate into the crystal. But I have no interest at all the damage on blah, blah, blah. Crystal is just used as a source of the virtual photon. Then please look at these pictures. So now, ion can feel the electric field made by the crystal. All the electric field come to you regularly. Then, let's go back to the fundamental concept of the photoabsorption. Photoabsorption occurs if the oscillating electric field frequencies or energies just match to the level difference of the specific state. Yes. However, if ions are moving in a periodic potential, this periodic potential is real potential made by the crystal. Then if you consider in a projectile flame, this periodic potential is really approaching to you. Then if this frequency is again matched to the resonance condition, ions will be excited. Okay? Then if you use a crystal, maybe the lattice length is the order of the angstrom. Then the ion's energy is the order of the close to the light of the speed. Speed of light. Then frequency will be the 10 to 18 hertz. 10 to 18 hertz means just X-ray region. So this is a kind of strange X-ray light. And you can enjoy such resonance using the array of the atoms in the crystal, or array of the atomic strings, or array of the crystal plane in three-dimensional way. Then how do you change this photon's energies? Just by changing the crystal angles with respect to the ion beam. You can tune the span of the crystal plane. So this crystal is just like a tunable laser in X-ray vision. Then the key issue is to change this direction. You can rotate crystal like this way or like this way. Then this is a two-color tunable laser in this sense. Then another interesting issue is this is a linearly polarized. So just by selecting specific crystal plane, you can polarize atoms more or less freely. And under the same geometrical configurations, crystal have many types of the crystal plane. So it's really the multicolor. Then if you think about the realistic condition to enjoy such physics, in this case, let's consider the hydrogen-like atoms from the ground state to the n=2 state. And this map shows as a function of the rotational angles theta or phi. Then every spot on this colored line satisfies such conditions. So that means high energy ion traveling through the crystal quite often excited by this phenomenon. And to observe these issues, okay, once it's excited to the higher excited state, these ions are more or less easily ionized because of the low binding energy in the crystal. So just by checking the charge state passing through the crystal, you can detect this phenomenon. Okay, so just after the passing through the crystal, we detected the charge state. Or we can measure the X-ray from the excited state. Then, very long day before, we just scanned this angle, and you can see at the resonance condition, really the survived hydrogenic atom is really reduced. So such phenomena is really happens anywhere. Then using this technique, now we can apply to the really the AMO physics. As I already told you, under the same geometrical configurations, ion can feel the different electric field, different photon, differently polarized. It's more or less similar to the case to use two types of the XFEL facilities at the same time. Then, of course, tune the energies. As I already told you, you can just rotate crystal. Very simple. Then again, we did the same experiment, but using these 3-level systems. So one photon is used for the coupling between the 2s state and the 2p state. Then such systems are load from the ground state. It's a really typical lambda type configuration. But the issue is, it's really X-ray energy regions, not the optical region. We use heavy ions. Then just by changing the coupling field, fixing the coupling field, and we scan the probed field, then as you can see, we can enjoy the very strange behaviors of the resonance. But this is not strange at all. It's very well-known structures as a ultratons doublet. It's a quantum optics. People are really frequently use this kind of concept. So this means that because of the very tight coupling between the 2s and the 2p, systems are combined as an entangled state, S plus P or S minus P. Then it's really decoupled. However, our photon is not real photon. Very strange crystal photon. So in a sense, it's a crystal dressed atom. Through these processes, crystal is behaving just to transfer the momentum to the ions. Anyway, from this difference between the two peaks, we can estimate Rabi frequencies, and we can estimate the intensity of this strange light. So intensity of this light is 10 to the 6 watt. So it's really equivalent to the intense lasers regions. Then, of course, it's specifically, as I already told you, it's linearly polarized case. So in a n equal 2 state, or 2p state, you have a 2p x, y, z, or 2p plus minus 1, 0. So you can couple to the specific n equal 2 state. So in this case, you can make a very strange shape, mushroom type wave function using this technique. Then just to monitor what types of the wave function are really we could monitor, you can change the polarization of the lasers. Then spectral change depending on the polarization. So this means, yes, in a crystal, traveling through the crystal, ions really oscillate like this way, the coupling of the S state and the P state. Then it's really coincide with the traveling frequencies between each plane. So it's really not a solid state physics, and we use accelerators, but it's really the atomic physics. Don't you think it's really one of the typical example of the AMO physics, I believe? Then I have only 5 minutes. Then I will quickly move to the forward. Of course, now we enjoy the dynamics, but these techniques also can enjoy the spectroscopies. So we decided to check the QED using this technique. And for this purpose, we decided to fly from Japan to Germany to use nuclear physics facilities. They can provide uranium atoms. And usually, this facility is used for the nuclear physics. But atomic physics is also very active. So we extracted the ions from the accelerators. Then I just showed. Anyways, again, using uranium atom, we could observe such resonance. We succeeded. However, they have a specific width. This energy width comes from the momentum width of the incident beam. That's the typical situations. If ions are stopped in ion traps, we have no problem. But it's already traveling and traveling. So we really suffer from the momentum width. But to avoid such broadening, we can use a technique of the ion storage ring. So we store these ions in a storage ring, and just passing through the flow of the electrons, we can cool these ion beam to the monoenergetic energy beam. The meaning of the cooling is it's really traveling fast, but the energy width is very narrow. So using such technique, we can easily cool down these traveling ions. Then, it's because of time? No? Yes? Really? Are you sure? Oh my God. Anyway, so using these techniques, you can get the more sharper resonance cases. So that's the typical way to use a cooling technique for high energy ion beams. So that's the all of my message. So this is one of the typical way of the AMO physics. Thank you very much for your attention.
Thank you very much. This sudden failure of PowerPoint was cutting you short. Sorry about that. Questions, comments, yeah.
And it's a very interesting technique. Just a couple of practical questions. I mean, I would worry about crystal damage, and also what is in a typical experiments, what's the survival probability through the crystal?
That's a very good question. Many people ask about the step. That, you know, we are using very high energetic ions. So it means atomic collision, atomic processes are more or less negligible. It's really the high nuclear physics region. So it's really passing through, almost no damage. we never experienced any damage because our energy is at 10 GeV areas, far from the atomic processes. Only this process survives.
Further questions? Yes.
It really is an intriguing technique, and you talked about it as if these things are phonons, but of course they look like phonons to the ions, but they're not real photons. And what I'm wondering is the fact that they're not real photons, does this have any real effect? That is, does it change anything about the selection rules for what kinds of transitions you can induce? And I presume that energy balance comes from slightly changing the translational energy of the ions. It probably isn't a very important effect, but the momentum transfer isn't the same as it would be with real photons. So I'm just wondering what kinds of effects come about because of the fact that they're not real.
Yeah, thank you. That's, again, very good questions. Very typical differences. For instance, real photon is really the polarization is really perpendicular to the direction of the propagating, of course. But this strange photon is, you can select any directions. So this is really not the photon. That's the typical issues. But the selection rule and blah, blah, or momentum transfer is really the same. Then now I have no time to explain the detail, but you can even think about in a picture of the band structures, like you explained yesterday, is using the typical band structures, and so the same concept is really valid.
But you would have the same kind of dipole selection rules? I mean, what
Yes.
would determine whether...
Yes.
So it's just a matter of what the symmetry is in the atom. You're going to get the dipole transition.
Exactly.
And,
exactly.
And it's not transverse, but on the other hand,
No,
guided waves aren't
that's
transverse
right,
either.
right.
So yeah.
Exactly.
I see no further questions. Thank you very much again.